Hello dear classmates, welcome back to the Testing Without Form Model chapter. In this video, we are going to introduce an interesting idea proposed by McCluskey, the pseudo-exhaustive test or PET. In this video, we will focus on the first PET technique, the individual output verification test. In the next video, we will introduce the second PET test, the segment verification. We all know that exhaustive test is very expensive in terms of test length. To apply an exhaustive test to a combinational circuit with n inputs, the test length is 2 to the power of n, which is exponential. The advantage of exhaustive test is that we don't need ATPG and we don't need for simulation. It's very suitable for built-in self-test because we need only a small counter. We don't need any pattern storage, and the fault coverage is very high. The only disadvantage of exhaustive test is that the test length is too long. But we can think about this question. Do we really need all the 2 to the power of n test patterns? Actually, in most of the case, we don't really need such a long test length. So McCluskey proposed a pseudo-exhaustive test. The idea of PET is that we don't actually need exhaustive test for the whole circuit. We can test each circuit partition exhaustively. There are two possible cases. In the first case, we can test each individual output exhaustively. For example, we can exhaustively test this cone of output O1, and we can test exhaustively the second cone for output O2. In this way, if we test each output exhaustively, then we can call it a pseudo-exhaustive test. In the second case, we can partition the circuit into segments. For example, in this figure, we partition this circuit into 5 segments. If we test each segment exhaustively, then we can test the whole circuit exhaustively. The total test length can be much shorter than 2 to the power of n. This is called the segment verification test, which will be covered in the next video. Now let's focus on IOV test in this video. If we want to perform IOV test, we need to check the structure of the circuit. There are two kinds of circuit. One is full dependence circuit or FDC. That means there are some outputs that depend on all inputs. For example, for this particular output, it depends on all n inputs of the circuit. In this case, the exhaustive test length is 2 to the nth, and the IOV test length is also 2 to the nth. In this way, the IOV test is not very useful for this kind of circuit. Fortunately, most of the circuit are partial dependence circuit or PDC. That means there is no output depends on all input. They can be something like this. For output O1, it depends on N1 inputs. For output O2, it only depends on N2 inputs. In this way, if we test the whole circuit exhaustively, we would need 2 to the power of N1 plus N2, which is a large number. But if we apply IOV test, we can test the Con1 exhaustively, which is 2 to the power of n1 plus 2 to the power of n2 for Con2. This number is much smaller than a true exhaustive test. In this way, we can significantly reduce the test time. So IOV test is useful for the PDC circuit, but it's not useful for FDC circuit. Here is an example of FDC circuit. This is an IC 74181, which is a very famous arithmetic logic unit, ALU. This was the first ALU on a single chip, and it was used in many historically significant mini computers. This particular IC has 14 inputs and 8 outputs. There are some outputs that depend on all the input. So the IOV test and the exhaustive test are all 2 to the power of 14. So IOV test is not particularly useful for this circuit. Here is another example, 74LS630. This particular IC is a 16-bit parallel error detection and correction circuit, which has 24 inputs and 6 outputs. Each output depends on only 10 inputs. So if we apply a true exhaustive test, the test length would be 2 to the power of 24, which is long. If we apply IOV test, we only need 6 times 2 to the power of 10, which is much shorter than the true exhaustive test. So IOV test is very useful for this IC. But can we do better than 6 times 2 to the 10th? Actually, we can. We can share test signals to further reduce the test length, because we can test each output simultaneously by sharing test signals. For example, on the right hand side figure, let's suppose Con1 and the Con2 do not overlap. So we can share the test signals T1 and the T2 among 2 different cons without any problem. So we can significantly reduce the test length from 2 to the power of n1 plus 2 to the power of n2 down to 2 to the power of maximum of n1 and n2. For example, on the right hand side figure, the number of input to the first con is 2. The n1 is 2. The number of input to the second con is 3. So n2 is 3. If we share T1 and the T2, then we would need a total of 8 test patterns instead of 4 plus 8. So sharing test signals reduce the test length. However, in practice, the input cons often overlap with each other. For another example, on the right hand side figure, we cannot share test signal T1 in this way, because here we have an overlap between Con1 and the Con2. If we share these 2 inputs, we cannot apply exhaustive test for Con1. So we must be very careful when we share text signals to avoid input of the same con. So McCluskey introduced the concept of dependency matrix to solve the text signal sharing problem. A dependency matrix is a matrix where each row represents an output and each column represents an input. The element Dij is equal to 1 if output I depends on input j. For this example, we have a circuit with 4 inputs and 3 outputs. So its dependency matrix has 3 rows where each row represents an output and each column represents an input. Because output F is dependent on input V, so this is equal to 1. And similarly, this is equal to 1. But output F does not depend on input Y, so it's 0. The row weight of the first row is equal to the summation of all the elements, which is 2. Similarly, the second row weight is 2 and the third row weight is 2. The maximum row weight W is the maximum number of input to an output in this circuit. For this particular circuit, all the row weight are 2, so W is equal to 2 in this circuit. We can now partition the dependency matrix in such a way that each row of a partition has at most one entry. This is because we do not want to share test signal with input of the same output. For the same circuit, we can partition this circuit into 3 partitions. Partition V, partition X, and the partition YZ. We can see that in each partition there is at most one in each row. So in this case, the number of partitions is equal to 3. The number of partitions can be represented by letter P, which means the number of test signals needed for this circuit. Please note that the way to partition a dependency matrix is not unique. For example, we can also partition this matrix into 2 partitions where V and the Y share the same test signal, and the X and the Z share the same test signal. Of course, smaller p is preferred because we want to reduce the number of test signals required. So this partition is better than the previous partition. Finally, the number p must be equal to or greater than w. What is the reason? Please think about it. For this example circuit, we already know that P is equal to 2 and W is equal to 2. We know that the number of test signal required is equal to 2. So that we can share input V and the Y with the same input T1, and we can share input X and the Z with same test signal T2. Now, the shortest test length is equal to 2 to the power of W, which is 4. In this way, each output is exhaustively tested. You can check by yourself. For output F, we have exhaustively 4 patterns. Similarly, for output G, it is also exhaustively tested. For output H, it is also exhaustively tested. So every output in this circuit is exhaustively tested. Now let's go back to our example 74LS630, which has 24 input and 6 output. We show the dependency matrix in this way. You can count the number of ones. For each row, the row weight is 10. So W is equal to 10. Now we can partition the dependency matrix in this way, where input 0 and 15 are in the same partition, 1 and 14 and 3 and 12, and etc. Totally, we have 10 partitions. So P and W are both equal to 10 in this case. If we want to test this circuit exhaustively, actually we do not need to apply 6 times 2 to the power of 10. By sharing the test signals, we can reduce the test length to 2 to the power of 10. Now it's time for you to work on this quiz. Given this circuit, please find the partition dependency matrix and figure out the number of P and W. Now please pause the video and work on this problem. Okay, have you finished? In this dependency matrix, we have 2 rows that represent output F1 and F2. Output F1 is dependent on 5 inputs. So W, X, Y, U, V, they are 1. For output F2, it is dependent on 4 inputs. So input W, X, Y, Z are 1. If we do a summation of all the row weight of first row is 5 and the row weight of second row is 4. So the maximum row weight W is equal to 5. Now let's do a partition. W input must be 1 partition. X must be 1 partition. Y is 1 partition. Z and U can share a partition because there is no more than 1 in each row. Finally, V is 1 partition. So we have 1, 2, 3, 4, 5 partition. Have you got it correctly? After we partition the dependency matrix, we now have P and W. In the following slide, we will show how to find the minimum IOV test. We know that the minimum IOV test length must be greater or equal to 2 to the power of W. What is the reason? This is because W is the largest number of input to a cone in this circuit. If we want to test this cone, at least we will need 2 to the power of W. So this is our minimum value. So can we achieve this number? The answer is dependent on 3 cases. If the circuit P is equal to W, then we are guaranteed to achieve this minimum value. In case 2, if P is equal to W plus 1, we can also guarantee to achieve this minimum value. However, if P is greater than W plus 1, then we may or may not be able to achieve this minimum value. So, in the following slides, we will describe these three cases in detail. In the first case, where P is equal to W, it is very easy to see that the minimum IOV test length is 2 to the power of W. As is shown in this case, we have two partitions and W is equal to 2. So we have two text signals, T1 and T2. And we can achieve our exhaustive test for each individual output in 4 test patterns. So for the first case where P is equal to W, it is obvious that we can achieve the minimum value 2 to the power of W. In the second case where P is equal to W plus 1, that means the number of partitions is greater than W by 1. For example, as is shown in this figure, the dependency matrix on our left shows that we have 3 output and 3 input, and we can have 3 partitions X, Y, and Z. So we cannot share test signals with any input. And the maximum row weight is 2. In this case, if we want to perform IOV test, we can apply a test signal Z equal to X inclusive or Y. In this way, these 3 test signals can be applied as the table on our right. We can see that any pair in this table is an exhaustive test. For example, the input XY pair is an exhaustive test, and Y and Z is an exhaustive test. Of course, X and Z is also exhaustive test. So we can apply IOV test within 2 to the power of 2, which is 4 test patterns. Generally speaking, if we have W test signals T1, T2 to TW, we can XOR them together to generate one more test signals. In this way, we can apply exhaustive test with test length 2 to the W. So, in the second case, we can also guarantee to achieve the minimum IOV test length within 2 to the power of W. This table is actually related to a very famous concept, orthogonal array. Orthogonal array was proposed by Rao in 1946. In orthogonal array, all the entries in the orthogonal array are from a finite symbol set. In our example, we use binary symbol set that include 0 and 1. For every selection of P columns, an ordered W tuple of symbol appear the same number of times, and W is called the strength of the orthogonal array. For example, the following 2 array shows orthogonal array with symbol set 0, 1 and the strength W equal to 2. We can see that a 2 tuple appear exactly 1 for every 2 columns. in xy, yz, or xz. We can see exhaustively two tuples, and each appear exactly once. The orthogonal array is not unique, so on our right hand side, this is also an orthogonal array. So we can use the orthogonal array to provide our IOV test for p equal to w plus 1. So how about the third case? In the third case, where p is greater than w plus 1, as is shown in this example, we have 6 outputs and 4 inputs, w, x, y, z. If you draw the dependency matrix and partition it, we will find that we need 4 partitions, and the maximum row weight is 2. So in this case, we can find the minimum IOV test like this. In this table, if we take w and the x 2 rows, we will see an exhaustive test. If we take x and the y, we also see an exhaustive test. The minimum test length is 1, 2, 3, 4, 5, which is greater than 2 to the power of w. So how can we find an IOV test for a given p which is greater than w plus 1? Is there any general solution? In McCluskey's paper, they provide a universal IOV test table. This table provides general solution for p greater than w plus 1. In this table, the symbol Uij represents a p-column matrix with all possible weight I and all possible weight j rows. So we can look up a particular number of w, then we would obtain the universal IOV test. And we can also look up the range of p or number of tests. For example, if p is equal to 4 and w equal to 2, we can look up this table and find 2 solutions where we have 2 choices. In the first choice, we have u0 p9 minus 1. In this case, p minus 1 is equal to 3. u03 means a matrix with 4 columns. Each column represents a test signal. And the first row is a row vector where row weight is equal to 0. And we have 4 rows where the row weight is all the possible combination such that the row weight is equal to 3. We have 1110 or 01111 or 1101 or 1011. Totally, we have 4 such combination of row vectors. And the solution is not unique. We can also have a second solution where we have u1p. 1 is the row vector where 1 represents 4 possible combinations of row vector such that the row weight is equal to 1. And 4 means the row vector where the row weight is 4. Either one of this solution is IOV test for this kind of circuit. Please note that the universal IOV table provides a general solution which might not be optimal solution. Sometimes we can find a better solution than the universal IOV table. For example, for this circuit where P is 5, W is 3, the dependency matrix is shown here. We can create an IOV test as shown in the right figure. You can verify for each output. For example, UVX. This is an exhaustive test because we have all 8 possible combinations. In this case, the minimum IOV test length is equal to 8, where it is 2 to the power of W, but is smaller than 2p. According to the universal IOV table, if W is 3, the minimum test length is 2p. But in this case, we can achieve a better solution than the universal IOV table. Now it's time for you to work on this quiz. Given the same circuit where P is equal to 5 and the W is equal to 5, so what case is this? Is case 1 or 2 or 3? And what's the minimum IOV test length for this circuit? Please work on this quiz. Okay, have you got it? Because P is equal to W, so this is case 1. And the minimum IOV test length can be achieved, which is 2 to the W. For the second question, we can achieve the minimum value, which is 2 to the W, which is 32. So, can we do this better than 32 patterns? Please see the next video for the answer. In summary, in this video, we have introduced the concept of individual output verification test. The IOV test every output exhaustively is one kind of pseudo-exhaustive test. And we answer 2 questions. First, how many test signals do we need? We can do a partitioned dependency matrix to find number of W and the P, where P is the number of test signals we need. And the second question, what's the minimum IOV test? If P is equal to W in the first case, we can achieve minimum IOV test within 2 to the W. If P is equal to W plus 1, we can use orthogonal array, and test length is also 2 to the W. If P is greater than W plus 1, in this case, we can use the universal IOV test table to find a general solution. But please note that this answer may not be optimal. Okay, before we end this lecture, we have one question for you. This FFT is quite simple. We said that P must be equal to or greater than W. So what's the reason? In our circuit classification, we don't consider P smaller than W. So why is the reason? Please explain. Thank you for watching.